Thank you for everybody's interest in this topic. What I'm going to talk about today is leveraging real-time vehicle modeling and talk a little bit about VI-grade's solution in that space. So as an overview, I'll talk a little bit about motivation to begin with, and the background on real-time modeling generically. And then I want to cover three different sort of use cases. We'll talk about real-time modeling for design studies and leveraging the speed of real-time modeling. Then I'll talk a little bit about steering system modeling for getting accurate torque feedback response. And finally, talk about integration with control systems and using a real-time plant model to further that. And then we can move to the Q&A session. So with that, let's talk a little bit about motivation for doing real-time modeling. Obviously, there's lots of pressure on vehicle development. There's reduced time to market. The cost that's available for setting up prototypes is always under pressure, both cost in money and also in time. And then there's also a growing necessity to have complex system integration where you're sharing models across an install base, across a build base between an OEM and the suppliers, all of which are putting more and more need to move sort of away from the classical physical prototype process to more and more CA-driven process. So if you look at that system integration, when it comes to doing vehicle level ride and handling analysis, for sure, there's three main pieces that have to be integrated to make that analysis work. You need, obviously, a model of the vehicle itself. You need a model of the environment that that vehicle is going to operate in. That means being a road model that you can have the vehicle interact with, potentially also interaction with traffic and other items. And then you need a way to actually drive that model, whether that's done on a simulator where you have a physical person driving it, or if it's done with a robotic driver that can actuate that model as an offline CAE tool. So VI-grade solution for that is called VI Car Real Time, and it's a complete solution. It provides an environment for all of those things I was just mentioning, and it's a great environment for setting up, building, analyzing, and post-processing vehicle response. It's a unique solution with a seamless integration to Adam's car. So if you're doing multi-body dynamics analysis, conversion to that can be done fairly well. We also have tools specifically designed for pulling in test-based data for things like K&C curves into the model. And it also has a unique robotic driver model that operates the vehicle through any kind of event, which actually has been a pretty successful product, even on its own, independent of Car Real Time. And then finally, an important thing for VI-grade is that the platform is very open. It's got strong integration. I hope you'll see some of that with third-party solutions, or whether that's software in the loop. And then if you don't know, VI-grade is a pretty large player in driving simulator space, and we use Car Real Time as the core of our driving simulators, and we also spend a lot of investment in making sure that it's an open, robust environment for doing that kind of work. So Car Real Time is our complete vehicle modeling environment for real-time virtual vehicle development, and that means both on a simulator, but also today's focus is much more on off simulator or just classical CAE analysis tool set. So with that, I would like to talk a little bit about the first first use case, which is using real-time models for design studies. I mentioned that we have strong integration with Adam's car, and I know there's a lot of suspension design work that's done in multi-body dynamics with that tool, or maybe Simpac or some others. But when it comes to doing large number of runs in a efficient way, it's hard to beat a real-time solution because they run so fast. Car real-time itself has got a full vehicle built up of all the subsystems that I'm displaying here. You can pull in the data and build a model. The key to the real-time modeling compared to, say, multi-body dynamics modeling, which are more generic tool set, is it focuses on using a reduced degree of freedom to make the simulation speed as fast as possible. In fact, faster than the actual clock speed, such that you can support a real-time environment like running on a simulator. But you can also leverage that same speed when you're doing offline studies where you have lots of runs to do and you'd like to do it on the wall clock as efficiently as possible. It's a full ride and handling capability tool set. For suspension design, it can break into either KNC curves as a way to reduce degrees of freedom. But you can also build models directly off of hard points and bushings and use that for parameters that are exposed to design studies. And then we have a built-in tool set specifically designed for doing large studies of runs. So for reduced degree of freedom, the models can run significantly faster than multi-body solutions for sure, and can even run, depending on the model that you build, sufficiently faster than real time too. So this is just an example of an output from I did a run on a lap of a track. The simulation lap took 66.5 seconds, but the actual clock that it took to run the simulation was 13.4 seconds. So something like 5 times faster than real time. That can be leveraged when you're doing lots of runs. So if you want to do a study where you're going to run hundreds of runs, but they only take a few seconds each, that is in itself a value. So how do you do lots of runs in a study? We have, well, first, over 25 built-in analysis events with a GUI that's standard that you can sort of select from a tree, and then each one of those analyses has a certain set of standard parameters that are defined by it that you can create. You can also take multiple sets of analysis and string them together into what we call a fingerprint, which you can treat as just a one submittal job that will run multiple analyses and generate all the results for you. And then finally, all of these events get defined out of the GUI through a file format that can be accessed by a utility called Event Builder, that you can modify those events, you can create your own, you can string multiple ones together. So it's very robust for setting up an analysis. So when it comes to suspension design, I mentioned that we can use KNC curves. And in fact, that's a big part of how real-time modeling is done so fast, is that the degrees of freedom in the suspension are reduced down usually to 2 per corner. It's the jounce or vertical response, and then it's the rotation of the wheel itself. And then all the other degrees of freedom get defined as KNC type curve lookups. But that sort of obfuscates a little bit the suspension design. That's great from a solver standpoint. But if you wanted to get access to things like hard points and bushings that feed into that compliance curve, they can also be modeled directly in car real time. And then what car real time will do is at the start of a job, it runs a pre-analysis to calculate the KNC curve and then proceeds with its standard real-time solution. And that's pretty straightforward. All the parameters related to the suspension, the hard points, the bushing rates, the curves are all exposed in a way that you can use them and modify them in a study. So one of the to do a study in car real time, there's a mode that's called it's investigation mode, and really what it is a tool set for setting up and running design experiments. So the way this works is you have a tree that exposes all the parameters in the model, and I pretty much mean all. There's over 1,000 parameters that you can get at. Typically, you need to have some kind of scale factor as a design input. So you can promote those whichever set you want, and then you can define what the study range that you're going to allow for that, a lower limit, an upper limit, a number of levels on it, or alternately, you can provide it with a table of fixed values that you want to do per parameter. So you define all of these factors as the things that you want the study to vary. And then you can define a response, as many as you're interested in. And then there's a utility to go in and look at all of the outputs that you would standardly get out of car real time. And you can expose those as a response and then have some function to try to reduce that down into a scalar value that makes meaningful use from a sort of DOE or study perspective. So you can take the average or the maximum or the RMS. And in fact, you can even define your own custom Python scripts to process the data to generate any parameter that you might be interested in. So once you've got that, then you can basically set up and run the study. You can tell it that you want to run live or in the background. You can push it out to multiple CPUs. If you really want to run a study in the cloud environment, we can work with you to get licenses set up to do that. And so when it comes to running a large study, when each individual run might take, definitely less than a minute, tens of seconds at most, you can run through a pretty large study that way. The last thing I'd like to say about this study process for anybody who's ever used Adams Insight, that's a tool from Hexagon that sets up and runs DOE studies in a generic way that interfaces with Adams. We read in and write out the exact same file format, so you can leverage that tool in car real time as well. So that's kind of one use case for car real time is if you're interested in just running a large number of runs, it's a great tool set for setting up and doing those kind of studies. When you get done with the runs, there's a HTML report that gets generated that maps out all the different inputs and back to the response points. It will spit out a table of results, and then all of the results files themselves are exposed in a way that you can get back at those results if you want to. And again, you can run that study on individual runs. You can run it on a fingerprint with a number of runs in them, different analyses in it. So that is what our investigation mode in car real time is. A really powerful tool, even for people whose focus might be on a more larger tool set like a multi-body tool set, to take a reduced model, run a large study, extract what the results are, and then take that back to that larger tool set is an excellent use of car real time and real time modeling. Okay, so the second topic that I'd like to talk about is steering system modeling to get accurate torque feedback. Car real time has a couple of different levels of steering model complexity you can build into it. The simplest one is just a map between the rotation of the steering wheel and the rotation out at the wheels that are being driven, whether they're front wheel drive or if you have a system that has rear steer, you can also do that. That's good for some use cases, but if you're interested in getting correct feedback torque calculated for the steering system, especially if you're looking at, for instance, steering assist and how to tune that. You need a much more refined model to do that. And so we have in car real time an advanced rack and pinion steering model that basically represents both the mechanical system and also the assist system for the steering, and its relationship back to the rack. The mechanical properties of the model get broken down in the car real time process, where you define the location of all of the joints, whether it's 2, 3, you can have more than that. What the relationship mechanically at the connection between the column to the rack is, and then all of the various pieces along that mechanical chain have the option of having both stiffness and damping, and for that matter, even a hysteretic frictional loop defined for them, that's appropriate for that subsystem. Now, once you've built that sort of a model up, you can add on top of that a steering assist model. You can do it internally. We've got a simple table that you can look up through a little bit of a gain equation that you can map in to get what that feedback steering assist response is to modify your torque response. Or you can turn that system off and turn on an external one, whether that's through a Matlab Simulink model that you've got a more detailed software in the loop process that you're working on, or from a FMI model. In fact, in the end, if you went to a simulator, you could replace that system with a hardware in the loop system as well. All of those are use cases that we worked hard with. And then once you've got all those mechanical properties, you know, there's a lot of redundant places where you could put damping or friction if you're looking at just input to output. So we go through a procedure with a couple of test cases that separate out the subsystems, and then the assembly that helps you tune in what each of those set of parameters are, such that when you're done, you'll get a nice data fit back to test data, so that the model, when you run it, is producing the right torque feel. So if you're on a simulator, this is a critical thing if you're interested in doing on-center feel of the steering system. But also, if you want to just get that same correct torque response out on an offline analysis, you can also do that. So that's kind of a second use case for steering system models. And then I would like to, as a third case, talk a little bit about control system evaluation with real-time plant models. You know, not everybody, when they're doing analysis, is focused on the full vehicle model. What they have is a subsystem that they're interested in, but they need a full vehicle plant model as a sort of boundary condition for that subsystem to do their development work in. Car real time has a standalone GUI, runs in Windows, but it also has a complete interface for Matlab Simulink models. So the car real time as a plant, the full vehicle model can be exercised as a S function that sits inside a larger Simulink model. And then we provide a library of many of the subsystems that you can either directly leverage, and you can turn off the internal car real time subsystem and turn on a Simulink subsystem that is equivalent or sufficiently similar. You can modify those subsystems to tweak them to be the way you like. You can get rid of them and have your own from scratch. So it's a very robust environment for working if you're already interested in doing plant work inside Matlab Simulink as an example. In that list of libraries, we provide them for all sorts of subsystems. This is just an example from a EV battery model that we provide. Again, you can replace them with your own. But typically, the way a subsystem works, this is just a screenshot showing the way you might take something like the steering column, steering system that we just talked about, but you have your own model that you would like to include in. You can go into car real time, into this S function, and basically you deactivate the internal system by feeding it some scale factors to just turn that system off. And then you extract out of that model the position and the rack force, and then feed back in the wheel torque and the rack displacement out of this subsystem model. And again, this could be a subsystem model that we provide and that you could modify there, or you can totally replace with your own subsystem. So that's true with pretty much all of the subsystems in car real time. One of the great strengths of car real time, in my personal view, is it's extremely open architecture. All the parameters are exposed and available. We don't try to lock up some IP and hide it away or anything. We know that different customers have different use cases on it. So here's an example using an ABS controller where we've, again, turned off the internal ABS controller inside car real time and replaced it with ABS control block that underneath the mask has got a fairly reasonable control model to play with. Another example where you might be able to use it. And then finally, I want to show one more example because it can tie back into use on a simulator. This is an example of taking the dampers and replacing them. And again, we've got a defined subsystem model with a lookup table that you can hijack and replace with your own. That is an environment shown here running offline. And then if you wanted to run on the simulator, you can replace that car real-time block with output and input blocks that will interface back to a real-time database on one of our simulators, so that now you've got that same subsystem model, but it's connecting back up on a live simulator environment. So car real time is it's a complete solution for doing real-time modeling, whether you're on a simulator or off simulator. There's a number of different subsystems used to build up that model. We've got a pretty robust robotic driver called VI driver that interacts with that. Very robust tire utility for interacting with different tires, and it's a very strong real-time environment. And the three use cases that I mentioned are all places where different types of customers can leverage, either doing large DOE kind of studies, but with computational efficiency. You can use it to set up steering systems and get proper feedback response if you're a steering system design engineer. And then the last example would be any kind of software in the loop or development that has an impact back to a ride and handling response where you need a plant model to interact with it. You can leverage car real time in a Matlab Simulink environment to use that as well. So I know that's a little shorter than the full hour time slot, but that's kind of the overview that I wanted to share. On the screen, there's some links that you can look at car real time, and then the right link talks about or should connect you to a page that will go over what our zero prototype process is. So with that's my presentation.